So last week we left off talking about Lewis structures, and then we didn't quite get to enthalpy from bond energy, so we'll do that now, and then we'll go through that. So this is chapter 9, and we'll finish that. Start chapter 10. So I will do this upstairs as a problem solving, but ammonium nitrite will do those upstairs for bond energies. Okay, so when bonds are formed, energy is released. Why is that? Okay, why is it exothermic? Well, if you think about it, when you have to break a bond, that's endothermic. You got to put energy in to break electrons away from nuclei. Does that make sense? So you're undoing Coulomb's law. So when you reform new bonds, you actually get energy back out. Okay, so you're taking an electron from one atom, and it becomes attracted to the nucleus of another atom, and so you have negative and opposite charges, negative and positive charges coming together, and that meets a potential energy requirement and energy released out of the surroundings. So remember this, recite it for me. Breaking bonds requires energy. Forming bonds releases energy. All right, just say it to yourself over and over. Write standards, like, punish yourself. Write it on a piece of paper 100 times over. Breaking bonds, endothermic. Forming bonds, exothermic. Okay, you get energy back out. And it goes kind of in line with the ionic bonding model with lattice energy. Okay, lattice energies are always exothermic. Why? Because you get cations and anions coming together, and that releases energy out to the surroundings. Okay, so it's all about positive and negative coming together, and you get energy released out. The difference between the energy released and the energy required to form and break bonds can be estimated as the enthalpy of the reaction. Right? So can anyone think of how we calculated enthalpy of reaction from chapter 6? We used a couple of different ways. We used Hess's law, and we used just standard enthalpies of formation, right? Remember that? So this is a way to estimate enthalpies of reaction, but instead of using heats of formation, we're going to use bond energies. Okay, average bond energies. So here are a bunch of covalent bond energies. You'll notice a couple of things, or I'll point out a couple of things. The energies are in kilojoules per mole. Excuse me. You'll notice that as you go from, say, a single bond, CC single bond, to a CC double bond, to a CC triple bond, you'll notice that the energies get higher. Okay? It means it takes more energy to break that bond, or you get more energy back out when you form that bond. Okay, so that should make sense, right? Triple bonds are stronger than doubles, which are stronger than single bonds. Does that make sense? All right, it's pretty straightforward. All right, so that's the main thing. You'll also, I just want to point out, for the CO double bond, they have a little star here. So 736 kilojoules per mole for a typical C double bond O. However, in carbon dioxide, okay, it's 799, not 736. So that's what this little star means. Okay, why do they have it for CO2 here? Why do they single that compound out? Well, it's because CO2 is the main product of combustion of hydrocarbons, and so it's so common that they specifically singled out CO2. Okay, what you also might notice is that if you look at HF versus HCl versus HBr versus HI, what do you notice about the bond energies? They decrease as the bond polarity decreases. So typically the more polar bond, the stronger the bond. Right, so that's something else you should be aware of. So where did these bond energies come from? What they did was they've done lots and lots of studies over the years. They've done a lot of calculations over the years. And what they've determined is that on average, these are the bond energies on average. But they are not specific to any one compound. So because they're not specific to any one compound, they're more of an estimate than using heats of formation. So if you had a choice between using heats of formation to calculate an enthalpy of reaction versus using bond energies, you would always want to use the enthalpies of formation because those are specific to the compounds in the chemistry. These are not specific to the compounds in the chemistry, they're just averaged bond energies over thousands of compounds. Okay. So a CH bond might be different in methane than it would be in a, say, decane, right? You remember the hydrocarbons? We kind of briefly touched upon it a long time ago. So the bond energies will change depending on the compound. So here's a learning check here. All right, so to break a CL-Cl bond requires 243 kilojoules per mole of energy. What would be the longest wavelength one could use to dissociate a single chlorine-chlorine bond? Okay. So this is actually kind of cool because it relates an old concept to a new concept. So the longest wavelength required to dissociate a Cl-Cl bond. Okay, so this is kind of cool. So if I have 243 kilojoules per mole required to break a Cl-Cl bond, so basically per mole of CL-Cl, okay, how much energy would it take per molecule of Cl2? All right, so for every 1 mole of CL-Cl, I have Avogadro's numbers worth of chlorine molecules. Oops, I left the units out here. So many molecules per mole. And so that would give me 4.04 times 10 to the minus 22 kilojoules per molecule of Cl2. So in other words, just to dissociate 1 molecule of chlorine gas, it would take this much energy. It doesn't sound like a lot, but we're only talking about 1 molecule. Okay, but for a mole of chlorine gas, it takes a lot more kilojoules. And do you remember the energy required? Do you remember the equation that we used to get wavelength, or relates energy to wavelength? Do you remember that from chapter 7? You're like, no, we don't. It's been weeks. Okay, so here's, you might recognize this. Okay, so the wavelength is going to equal to Planck's constant divided by the speed of light in the vacuum, and then we have delta E atom. But in this case, we're going to say delta E molecule because it's chlorine as a molecule. Okay, so this energy here is our delta E per molecule of Cl2. So running the numbers here, Planck's constant 6.626 times 10 to the minus 34 joules seconds times the speed of light, 2.998 times 10 to the 8th meters per second. And then we have, and it's asking us what is the longest wavelength. Okay, so what are the units of wavelength typically? Nanometers, right? Going from nanometers to meters, we know we have 10 to the minus 9th meters for every 1 nanometer. Right, so the seconds cancel, the meters cancel. And then we have this 4.04 times 10 to the minus 22nd kilojoules. And then we got to get that into joules. So we have 10 to the 3rd joules per kilojoule. And now the joules cancel. So this wavelength comes out to be 492 nanometers. What color do you think that is? What color of light do you think that is? So like green is like over 500. You might remember your hydrogen spectrum from a week or two ago. So it might be somewhere. It might be kind of like blue. So you can use light to dissociate bonds. Okay, and I used to do this all the time in my research when I was a grad student. We used lasers to blow molecules apart. Okay, but if we didn't meet that minimum energy to dissociate that bond, we wouldn't see any signal, right? So we had to use a wavelength to dissociate chlorine, for example. All right, any questions on this? This is kind of cool because it takes bond energy with an old concept, factor 7. So check out this video. Okay, this is a reaction of chlorine gas with hydrogen gas initiated with laser beams. Really cool stuff. Oh, I need to. Hang on a second. Is the sound on this? Oh, it's on. Okay. All right, hang on. Is this the volume is really low? So you've got hydrogen gas and chlorine gas.
Hi. Today we're going to burn hydrogen and chlorine together. We're going to initiate a reaction that's going to drive this torque all the way across the room with a little bit of ultraviolet light from an LED flashlight that I carry around with my work keys. This is a quartz test tube, and it's held in a 3-jaw clamp, small stand. Got a to carry on your keychain, LED light, and that much light initiates the reaction by splitting up chlorine molecules into chlorine atoms so that a free radical chain reaction can take place, which is why this is such a dang fast reaction. We're also recording in high speed, 480 frames per second, with a little cheesy there, and we're going to see whether we can actually see the reaction happening in slow time. Okay. So here we go. We're going to work up from red photons to ultraviolet photons. Red light, no reaction. Yellow, a little more energetic, still no reaction. Green, bright but no reaction. Blue, sometimes works. Ultraviolet, boom. Usually it bounces up into the seas. There it is. Ooh, I found it.
All right. So you guys videos like that all day, right? Right, so so what's going on there is they're using the light dependence. You need enough light to break this bond so that these chlorine atoms, he mentioned the word free radicals, right? So when you use that ultraviolet light to break the bond, then these chlorine atoms, which are called free radicals, can then react with the chlorine, can react with the hydrogen gas to produce the hydrogen chloride, right? And as he was saying before, free radical chemistry is quite expedient, you know. So free radicals are just Lewis structures basically with one unpaired electron, right? One dot, and those are incredibly reactive. So I was doing a lot of free radical chemistry in my research, and it's a lot of fun, but it's hard to detect them before they react, so you got to use the uncertainty principle to your advantage to do that. So, cool stuff. I don't know, what do you think?
That's cool.
You know, so my goal was to show you a bond energy, show you a calculation how you would need a certain wavelength to do that. He said that blue sometimes works. Okay, so maybe the blue light that he had was not intense enough to initiate enough of a reaction. He just had a really low intensity diode from his keychain, right? But I have a blue laser pointer at home that I believe would probably work, you know, because it's actual really bright laser. Anyway, I thought that was cool. So you see the wavelength dependent. if you had a green wavelength or yellow or red, not enough energy to dissociate that bond. You know, and so I just wanted to illustrate the idea of bond energy, which I think is really cool in that video. All right. So instead of using bond energy, so you can always use heats of formation, right, to do this. So you remember this table? All right, cool. Okay, so what are the equations you could use to compare? So you've got the enthalpy of reaction is equal to the sum of the products minus reactants for the heats of formation. This should look familiar to you. What's new is you can also estimate delta H reaction by taking the sum of the bond energies of the reactants minus those of the products. What do you notice that there's a difference between these two? What do you notice the differences? They're flipped, right? This is products minus reactants. This is reactants minus products. Okay, so really important to keep that in mind. Okay, so let's do an example with ethane, and then we can move on. All right. So it says here, calculate the reaction enthalpy for the combustion of ethane, and they give you the structure for ethane there, using heats of formation and average bond energies. Okay, the structure of ethane is given below, which value is more accurate. I'll just do the bond energy version, you know, and then you've done the heats of formation before, so I'll just use the answer from that to compare and contrast. So what do we have to do first? We need to get the chemical reaction, right? So if I write a reaction of ethane, what's it going to react with for the combustion? It's going to react with oxygen, and I'm going to form what? Yeah, CO2 gas and water vapor. Okay. Okay, and then ethane. Let's see here. Also, call it a gas. Okay. So what do we do from here? If we want to use bond energies, we have to look at the structure. So let's do the structures. So it gives us ethane already. Alright, so there's ethane. Lewis structure for oxygen had a double bond in it. CO2 had 2 double bonds in it. So you can see how you kind of need to do Lewis structures just to get here, right? And then for water, that's the Lewis structure for water. Okay, what do we do need to balance this reaction. So let's go ahead and balance it. Turns out that if I balance it, let's see, if I do 2 carbons, 6 hydrogens, 3 here. Okay, then we look at the oxygen, we've got 7. So that would mean 7 halves, but we don't like halves. So I'm just going to take 7 and then multiply the whole reaction by 2. So it's going to be 2, 7, 4, and 6, right, for my balanced reaction. Okay, so what we have to do at this point is we have to say, okay, we're going to take the coefficients and multiply the bond energies by those coefficients. Alright, that's what we're going to do. Are you with me? Have I lost you yet? Yes. Okay. Anybody, if you're lost, ask a question. So I just took the combustion reaction, balanced it. I'm looking at the individual molecules now, writing Lewis structures, and I know I've got those coefficients from the reaction in front of us. Okay, maybe as we go along, if you're lost, it'll come together. Okay, so what we have to look at is we have to look at all the bonds together. I have the sum of my reactants minus my products in this equation. How many CH bonds do I have in this compound? I've got 1, 2, 3, 4, 5, 6 CH bonds. So I'm going to say 2 times 6 CH bonds. And I'm going to add that to 2 times the 1 CC bond in there. And I'm going to also add that to the 7 oxygen bonds. There's only 1 bond per molecule of oxygen. So I've got that. And those are my reactant bond energies. I'm going to plug in the bond energies from our table into this equation. Okay, minus the products, so it's reactants minus products. I've got 4 for my coefficient times 2CO double bonds plus 6 times 2 OH bonds from water. So, just to reiterate, these numbers here are the 2 okay, so the coefficients come first, but then we also have to look at how many bonds are in that molecule, right? So that's where that comes from. So is everybody all right with that?
Good question. I'm sorry, I was writing when you were putting the second number, those are the number of bonds. So like the 4 and the 2 for this C double bonded O, and that's because it's a double bond, is that correct?
It's not that it's a double bond, it's that there's 2 of those bonds in the molecule.
Oh, I see, okay.
So it's 4 for the coefficient, that's this 4, which is this 4. But then there's 2 CO bonds in the molecule. So there's a C double bond O here, and also here.
Oh, I see.
There's 2 bonds in the molecule, and that's why I'm multiplying here by 2.
That makes sense.
Okay, same idea with the ethane, right? I've got 6 CH bonds, so here's the coefficient of 2 times the 6 CH bonds.
Okay.
Right there. For here, there should be, I didn't put the 1 in there. You just write that just for consistency. Okay, this is a 1 because there's only this one CC bond in here. Right. So the first number I have there is for the coefficients. The second number is how many of that bond type are in that molecule. All right, and that's what these two numbers mean. So at this point, to plug and chug, we can just take the bond energies from our table. So let's go back to our bond energies. So at this point we'll have 12, all right, 2 times 6 is 12. Bond energy for a CH bond, if you look at the table there, for a CH bond, it's 414 kilojoules per mole. Now remember, this is 2 times so many moles of bonds, so really this is moles too, and so the moles will cancel. Okay, and you're just going to get energy from this. We've got 2 times the CC bond. So if you look up a CC bond in that table, you should find 347 kilojoules from that. You've got 7 times the OO bond. Okay, for an OO double bond, you should find 498 from the table. We've got 8 total CO bonds, or C double bond O. In carbon dioxide, you look at the table, it says 736 for a C double bond O, but then there's that little asterisk there for CO2. So what should it be for CO2 here? 799, right? 799 kilojoules specifically for CO2. And we have 12 OH bonds. So OH from the table is going to be 464. So again, reactants minus products. Okay, if this was using heats of formation, it would be products minus reactants. Okay, but it's reversed. Okay, so from this, just from the reactants, we would get 9,148 kilojoules. And for the products, we would get 11,960 kilojoules. Okay, so subtracting these, you would get a negative 2,812 kilojoules. So if we wanted to assign that delta H to this reaction as written, it would be negative 2,812 kilojoules. You know how when they write thermochemical equations, they just write the balance equation with a delta H next to it? They use that format. So that would be the delta H that they would put next to it. Okay, now this is, to keep something in mind, this is the energy for every 2 moles of C2H6 that gets combusted, because the coefficient was 2 for ethane. What would it be for 1 mole? It'd be half of that, right? So delta H for the combustion of 1 mole of ethane would be negative 1,406 kilojoules. So the final answer, I would say, just to keep it per mole of reactant, you would say negative 1,406 kilojoules per 1 mole of C2H6O. I mean C2H6. So if you had to do a reaction or a problem where it asked, well, okay, how many grams of ethane is required to get so much energy out.